us a numerical on the series resonance. Through this numerical, you can understand what happens at the resonance frequency and above the resonance frequency and below the resonance frequency. Okay, so sorry, this is it should be a resistance first. So this is a resistance. Capacitor. Okay. So this is the 10 ohm resistor and this is the 0.1 Henry, 0.1 Henry, 0.1 Henry. And this is 10 microfarad. Okay. So what is the resonant frequency? We know resonant frequency Fr equal to 1 by, this is the formula you all know, this is 1 by 2 pi into LC. Okay. So just put the formula over here. Just 1 by 2 pi root over of LC. Look, L is 0.1 Henry. 0.1 Henry into, this is the microfarad, into 10, and this is the microfarad, means 10 to the power minus 6. 10 to the power minus 6. Okay, so it will give you 1.159.2 hertz. Okay, this is the resonant frequency Fr. Now at the 10 hertz below, we have to find out the at the 10 hertz below frequency and the 10 hertz above frequency, and then find out the X reactance at 10 hertz below and 10 hertz above, and we have to find out the inductive reactance at the 10 hertz below and the 10 hertz above. So if this is our resonant frequency, then we have to find out the 10 hertz above. 10 hertz. Above, 10 hertz above means just add 10, means 169.2 hertz, and 10 hertz below, 10 hertz below means what is 145.2 minus 10 is 149.2 hertz. Okay. The impedance at the resonance is equal to the 0, because we have just seen this impedance at the resonant condition is just like this, because XL equal to XC. Okay, this would be the 0, because this is equal. So ultimately it's become R. Okay, so the capacitive reactance at this condition, capacitive reactance as this condition is XC1 at 149.2 hertz. It is given as XC1 equal to 1 by, this is 1 by omega c, and it is given as 2 pi 2 pi into 149.2 into 10 to the power minus 6 into 10. Okay. So it is giving you, it will giving you 1.06.6.6 because this is the ohm. Okay. And capacitive inductance it is C2 at 169.2 hertz. It will be giving you just like this 1 omega to C. It is giving you 2 pi into 169.2 into 10 into 10 to the power minus 6. Okay. This is the capacitance and this is the frequency. This is the capacitance value and this is it is for a microfarad. 10 to the power minus 6 multiplied due to the microfarad to farad. Okay. It will give you that 94.06 ohm. Okay. And now we have to calculate the inductive reactance. Okay. So the inductive reactance. Inductive reactance. So we know that is XL1 equal to omega 1 L. So this is omega equal to 2 pi into 149.2 into 10 or that is the inductive value. So it is giving you 93.75 ohm. Inductive reactance. So inductive reactance, and this is 149.2 hertz. Okay, and if we want to calculate 1.2 hertz, XL2 equal to omega 2 L equal to 2 pi into 169.2 into 0.1 equal to, if you multiply this, you get this is 106.31 ohm. Okay, and now find out the impedance. This is, we have find out the capacitance, means capacitive reactance. We have find out the inductive reactance. Now we have to find out the impedance. So impedance at 1.492 hertz. Okay, means impedance Z at 149.2 hertz. So it will be giving you. So here HC is greater than, you can see HC, this is the HC and this is the XL. So HC is greater than XL. So this is called the capacitive impedance. Capacitive impedance. What is this? This is this term. This term will be giving you 1.6.28 ohm. Okay. And now we have to calculate the impedance at the time of 169.2 hertz, means 10 hertz above. So okay, so if you put this value, this is 10 square plus, you can see what is the xl2. We have find out xl2 is just like 106.31 minus 94.06 square. Now here XL is greater than XC, because above the resonant frequency XL became the higher. So XL greater than XC. In before that, XC greater than XL. Now XL greater than XC. So this is called inductive load. This is called inductive impedance. Z equal to this idea. This is 15 15.81 ohm. Okay, here XL greater than XC. So impedance is inductive. Okay. So next we are going to the discussion according to the bandwidth, etc. Okay. series resonating circuit. What is the bandwidth? Look, bandwidth, what is the bandwidth? The frequency band within a limit of the lower and the upper half power frequency is called the bandwidth of the resonant circuit. You can write down just this is for just recall. The frequency within the limits of lower and upper half okay, on this resonance circuit. The response of the resonating circuit within this bandwidth is assumed to be A to be F. Okay, and this is the flat. Within this resonant frequency, the bandwidth is the flat. This is the flat. Just it is going this way and this way. Okay, and for the parallel, you can see this is in this state, and in the series, this is the this state. Okay, so you can remember this for the series circuit. This is a band pass, and the parallel circuit it will be the band reject. Okay, just remember this. And now coming to the selectivity. And you can see, you can just remember whenever the smaller is there, then this is the bandwidth. If the larger R is there, then this is the bandwidth. This is for the smaller and this is for the larger R. Okay, this is the bandwidth. This is cutoff frequency, this is cutoff frequency, and this is also for cutoff frequency. This is also for the cutoff frequency. And what is the effect for the smaller? The steady state is just like this, but this is the smaller because damping ratio is very less, and it's a larger. This is for this is the system. Okay, and now come to the point of selectivity. selectivity and the visible bandwidth. So what is selectivity? Selectivity of a resonating circuit is defined by the ratio of F0 means F naught to the bandwidth of the circuit. So selectivity, it is given by the ratio F naught and this is the F. So this is also called the Q factor. Okay. Now F1 and F2 also called the 3 dB points as the current ratio I1 by I0. And what is the 3 dB? dB means the ratio. This is 20 log 10 base I1 by I0 equal to, we can write down 20 log 10 base 1 by root 2 this. Okay. So I1 is lower than I0 by the 3 dB, and similarly frequency F1 is also lower than the frequency F0 by the 3 dB. Okay. So the power dissipation at the F1 and F2 would be the half of the